So we've learned all about parallel circuits and series circuits, but next we're going to put those things together to solve complex circuits. So circuits like this that have sections that are in series, sections that are in parallel. And here we're going to be asked to find the current, voltage, and power through every resistor on this circuit here. So we've got 120 volts of voltage coming from our battery, and then it's going to meander around the circuit and come back to our battery. We want to find the voltage drop, the current, and the power through each resistor along the way. Okay, so to solve this, the first thing you need to do, first you need to find our total. If you know every resistor in your circuit, you can combine those to find our total. So that's a really good way to start. To find our total, what you want to do first is look first for resistors that are in series with each other. So like resistors like this. So R1 and R2 are nicely in series. This is a little bit messy here, right? So there's this R5 is not in series with anybody, but he looks like he's in parallel with these two. So what we want to do is combine the things that are in series. So R3 and R4 are in series with each other, so we could combine those ones, and then we just pause there. And these two are in series with each other, so we combine those ones. And then once we've combined everything in series, we kind of stop, see what it looks like, and see what else we can combine. And what we usually see at that stage is there's a bunch of stuff in parallel that we can combine next. So we're finding our total. You want to find or combine resistors in series first. And then we look for ones that are in parallel. Okay, so here's our circuit. Ones that are in series, R1 and R2 is one set. So what I do is I redraw my circuit here. So here's my battery. And I draw R1 and R2 together. So I literally call this R1 and 2. And the rule for series resistors is that the resistances just straight up add. So the 2.85 ohms will add to 2 ohms, and the resistance of R1 and 2 together will be 4.85 ohms. So that's another reason why it's nice to start with series, is just because it's also easier. Okay, next we kind of go up here, and then at this juncture things split off. R5 goes this way, R3 and 4 go the other way. So I'm going to have R5 here. R5 is 6 ohms. I can't combine him with anyone because it's not in series with anything. Then up here I have R3 and R4. R3 is 1.5 ohms, R4 is 2.5 ohms, so those combine to make 4 ohms. So here I have R3 and 4 is 4 ohms here. Okay, then we carry on. I have an R6, which was 1 ohm here. R6 isn't in series with anyone. You can tell that on either side of R6, right, there's a juncture, things split off. If you see things splitting off on either side of your resistor, that just means it's not in series with anybody. So after R6, kind of go this way. Then I've got this R7 in here. R7 is 5 ohms, not in series with anything. And on this side I have R8 and R9. These guys are in series with each other, so I can combine both of those. So 5 and 10 ohms, that's going to make a 15 ohm resistor right here. So R8 and 9 is 15 ohms. Cool. Alright, the next thing you want to do is look for any resistors that are in parallel and combine those. So our next move is going to be combine resistors in parallel. Next, so I'm going to look for any resistors that are in parallel. My pen's kind of dying here. Let's see if I can get us a better one. Okay. So I redraw my circuit again. So I'll draw it down here. Here's my battery. This guy is not in parallel with anyone, so I just redraw him again. So there's my R12 is 4.85 ohms. But then these two here, you can see the junction splits here and then rejoins, and R3 and 4 is nicely in parallel with R5. So I can combine those into a single resistor. And so I do. The single resistor looks like this, and I call it R13. 3, 4, and 5. So these two combined into one, call R3, 4, and 5. We'll calculate what that is in just a sec. Next I've got R6 here. R6 isn't in parallel with anyone, so I just write him down. R6 is 1 ohm. And then R7 and R8 and 9 are nicely in parallel with each other. So those two I'm also going to combine into one resistor, which I can call R7, 8, and 9. Okay, now we need to start calculating these resistances. So let's look at R3, 4, 5. So these two that are in parallel, how do they combine? So remember that in parallel, your resistances don't just add, you use this formula here for parallel resistors. So 1 over R3, 4, 5 will be 1 over this resistor, the R3, 4, plus 1 over R5. Let's plug in our numbers here. 1 over R3, 4, 5 is going to be 1 over the 4 here plus 1 over 6. I want to get a common denominator here, but if you're feeling lazy, you're welcome to use your calculator. Just do 1 over 4 plus 1 over 6. That gives me 5 over 12. Now you're not quite done yet, so be careful. You haven't solved for R3, 4, 5 yet. You solved for 1 over R3, 4, 5. So that's 5 over 12. We have to flip both sides of this fraction in order to get R3, 4, 5 on the top. So R3, 4, 5 is going to be 12 divided by 5, which is, as a decimal, it's kind of nice to have decimals, 2.4 ohms. All right, so I can write that in here. So that's 2.4 ohms. Next, I do the same thing with R7, 8, 9. So I'm combining R7, which is 5 ohms, with R8, 9, which is 15 ohms. So I combine it in the same way. So 1 over R7, 8, 9 will be 1 over R7 plus 1 over R8, 9. That's going to be 1 over 5 plus 1 over 15. Need a common denominator. Multiply this by 3 over 3. So that gives me 3 on the top here plus 1, or 4 over 15. And that's equal to 1 over R7, 8, 9 though. So I need to flip both sides of that fraction. And I get R7, 8, 9 on its own will be 15 divided by 4, which is 3.75 ohms. Okay, so I can write that in over here, 3.75 ohms. Now you should always end up with a nice series circuit like this. So just resistor, 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 all in series once you've combined everything that was in parallel. So my last move is just to combine all of these resistances, and they're all in series now that I've simplified my circuit. So our total, it's just going to be add them all together. 4.85 plus 2.4 plus 1 plus 3.75. Okay, so my 3.75 plus 1 plus 2.4 plus 4.85. And I get 12 ohms. So our total is 12 ohms. All right, we're not actually completely done with this picture, but we put it away for now. We're going to go back to our original circuit diagram here. And the next thing we do is we start to solve the actual circuit. So your first step is just to write our total where it belongs. So our total is the total resistance of the entire circuit. So you're going to write it with the battery, because the battery is sort of the information about the whole circuit. So our total is 12 volts. Next, what we're going to try and do is slowly work out the current in each place. Every time you have 2 of 3 things, you can find the third. And the equation we're working with is this one. Delta V, the potential, is I times R. So if you know delta V and I, you can find R. If you know I and R, you can find delta V, etc. In this case, I know delta V and R, so I can find I. I'll just rearrange this for that. I will be delta V divided by R. So in our case, whenever you're using this equation, right, where you're going to use it for a specific resistor or for the battery. So if you're so make sure your subscripts match. So if we're talking about delta V total and R total, we're going to find I total, which is the current through the battery. So the current through the battery will be the delta V total, the delta V across the battery, divided by R total. Plugging in our numbers there, that's going to be 120 volts divided by 12. Oh, that should have been ohms, sorry about that. 12 ohms is the resistance, sorry. So 12 ohms on the bottom there. 120 divided by 12 will give me 10 amps. So I total is 10 amps. So my next move is going to be to start solving the rest of the circuit. I want to look where else in this circuit would I have 10 amps. Remember to think about current as being like the number of people walking along a path, or in this case it's actually the number of protons, because we pretend that protons move, walking along our wire, or moving along our wire. I guess protons don't really walk. So if I have 10 people walking this way, well, there's nowhere else for them to go. All 10 people have to walk through this resistor, all 10 people have to walk through that resistor. So that automatically tells me I1 is 10 amps, and I2 is also 10 amps. All right, so next I can start solving for the voltage. So as soon as I know two things, right, I can find the third. So delta V1 is going to be I1 times R1. So I'll do my 10 amps times 2.85 ohms, which will give me 28.5 volts. And similarly, delta V2 here is going to be I2 times R2, or 10 amps times 2 ohms, which will be 20 volts there. All right, so now we have a tricky situation. So we've come along, 10 amps go this way, 10 amps come here, and then they split. So some will go this way and some will go that way. But it's not going to be like 5 and 5, because I wouldn't want 5 amps to go this way and 5 amps to go that way, because this way is actually easier, right? Overall, 1.5 ohms and 2.5 ohms, this adds up to 4 ohms. This is a lot easier than to take the 6 ohm route. So more of the current is going to take this route than that route, but I don't know how much more. So what I need to do is actually go back to this picture here. This picture of my series circuit is actually a really helpful one, because I can use it to get the voltage drop across every single section, even though this isn't a single resistor and it's actually this whole cluster of 3 resistors, right? I could still find the voltage drop from here to here. If I call this point A and this point B, I could draw point A and point B on this circuit. They would be here, A, and B. And remember that voltage is just like a height drop, a difference in potential from one position to another position. So the height drop from A to B will be the same whether I'm considering all the different paths or whether I've simplified it to just one path. It's still the same height drop down the mountain. It's kind of like there might be many ski routes down the mountain, but the distance from the top of the mountain to the bottom is the same. So I can use this picture to find that height drop or that voltage drop, and then I could go back and use my voltage drop in the full circuit picture. So that's what we're going to do. What I'll do is I'll write in the current through each of these sections. So the current through I1 and 2, because this is all in series, the current everywhere will be 10 amps. So the current is 10 amps there. The current in section 3, 4, 5 is 10 amps. What that means in terms of this picture is that through both of those paths, 10 amps will flow. Some will go that way, some will go that way. Maybe 4 amps goes this way, or maybe like it has to be more than half. So maybe 6 amps goes this way, maybe 4 amps goes that way. Right? We don't know how much, but we just know that 10 amps overall goes from point A to point B. There's going to be 10 amps through here. I6 is 10 amps. And there's going to be 10 amps through here. So I789 will be 10 amps. So that's really helpful because that lets me actually calculate the voltage drop across each of these sections. So delta V12 will be 10 times 4.85. So that's 48.5 volts. Delta V across this section, 3, 4, 5, is going to be the 2.4 times 10 amps, or 24 volts. The delta V6 will be just 1 times 10 amps, or 10 volts. And my delta V789 is going to be the 3.75 times 10 amps, so that's 37.5 volts. This is a really good chance to just do a quick sanity check and make sure you've gotten some key things right. So if you gained at the battery, right, the delta V total is 120 volts. So that means that the battery, I gained 120 volts. and then I slowly lose the 120 volts as I go around. So what I can do is actually check if this worked out. I should do 120 minus the voltage drop here, so I lose 48.5 volts here, and then I lose another 24 volts here, then I lose another 10 volts here, and I lose another 37.5 volts here, and I should get down to 0. And sure enough, I do. So that means that so far we've done things right, so that's kind of encouraging. The other thing you can check is that this one, R12, we've actually already calculated voltages across each resistor. We know the total drop from the beginning to the end of that is 48.5. So we can look at our individual voltage drops, 28.5 and 40 volts, and that total drop should be 48.5. And sure enough, 28.5 plus 20 is indeed 48.5. So far we're doing things right. This is good. Okay, the next thing we can do is look at this section from A to B. What we see is that you drop 24 volts from A to B. So now I can go back to this picture and I know that I dropped 24 volts from A to B. So on this path that doesn't really help me because there's still 2 resistors. I drop, some of the 24 here and the rest of it there. It's not enough information. But in this direction it is enough information, which is really nice. So I know that delta V5 is 24 volts, because to get from A to B I have to drop 24 volts, and that's the only resistor on that path from A to B. So this will be like maybe some of the 24 volts, maybe like 10, and then this is 14, right? I don't know how it's split up there, but I do know that all of the 24 volts is dropped along that path because it's only one resistor there. That lets me find the third thing, right? That lets me find I5. I is going to be delta V5 divided by R5. So it's going to be your 24 divided by the 6, which is, 4 volts there. That's great. So, or 4 amps, sorry, 4 amps. I'm like messing up my units today. 4 amps is going to go this way. Okay, now we have to think about our current and what's happening with current. So if 10 amps comes in this way, and then 4 amps comes off and splits off this way, how much must be going ahead? Must be 6 amps, right? We think about amps as like the number of people walking down a path. 10 people walking down this way. If 4 of them take this route, then 6 of them must have taken the route going straight ahead. So that automatically tells me I3. I3 is the 10 amps minus the 4 amps, which is 6 amps. So this also fits our intuition. This path has less resistance than this path, so it makes sense that more current is going to flow down this path than this path. And now I know it's exactly 6 amps more. That's another thing that I know. So I know 2 out of 3 things, so I can find the third, delta V3. It's going to be I times R, so it'll be 6 times 1.5, which is 9 volts. Sorry, 9 volts. My pen isn't great. Then I've got I4. So if 6 people are walking down this path, there's only one place for them to go here, right? They all have to go down that path. So I4 is also 6 amps, and that tells me delta V4, which will be 2.5 times 6, and that's 15 volts. Let's just pause for a quick sanity check. If it's a drop of 24 volts from A to B here, then this should also be a drop of 24 volts. So we drop 9 volts through the first resistor, and then another 15 volts through the last resistor. That's a full drop of 9 plus 15, which is 24. So it's working out, so this is good. Okay, next at this juncture, the current comes together. So 6 amps is coming from here, 4 amps is coming from there. So together, those must add together to be 10 amps again. So we're back to all 10 people walking together along this route. So I6 must be the addition of the currents into that intersection. So it'll be the 6 amps plus the 4 amps, which is 10 amps. Now I know I6, I know R6, so I can find delta V6 right away. So 1 times 10, right, which would be just 10 volts. Great. Our last section, so we're almost there. So there's a few ways you can think about this last section. You can go back and use this picture. You've already found the delta V across this should be 37.5. If you didn't have that, another way you can think about this is to choose any single loop around the circuit where the current would flow. So the current's going to come from the battery like this. And let's take this path because it's an easier path. It's just a little simpler, but Either path would work, any path that you pick works, as long as it's a nice loop. Sorry, my battery died there. Just restarting. I had to redraw things. I took the opportunity when I was redrawing things just to clean up my significant figures. You'll notice there's three sig figs, everywhere. So I just put all of my answers in 3 significant figures too. Just looks a little bit nicer. All right, so we've made our little loop from the battery this way and back here. And again, you could draw any loop you want. You could draw this one as well. So one way we can find the voltage drop across R7 is to use the fact that we know we gain 120 volts at the battery, and I have to lose all 120 of that by the time I get back to the battery on any loop that I take, any path that I take. So first I lose 28.5 volts here, and then with the next resistor on my path I lose 20 volts. And then I'm going to take this path, so my next resistor I lose 24 volts. And then this way here, I lose another 10 volts. And now I have a height of 37.5 volts that I have to lose before I get back to the battery. If I'm taking this path here, there's only one resistor that I can go through to get home now. And so I have to lose all of that 37.5 volts to get home. So this delta V has to be 37.5 volts. I knew that from this picture already, right? We already knew that that drop was 37.5 volts, but it's just a good way to check. It's so easy to make a small mistake in these kinds of problems, so if you can solve things more than one way, that's just a really, really great idea. All right, we want to get I7. We know, remember that delta V is IR, so I is delta V divided by R for any given resistor. So for this one, that'll be delta V7 over R7. So that's my 37.5 divided by 5. Gives me 7.5 amps. Okay, next I can think about, well, what would be my current through here? I know that 10 amps is walking down this path, and then 7.5 of them go this way. So how many must have gone forward? Well, it must be the rest. 10 minus 7.5 would be 2.5 amps. So we must have I8 here, the current through this resistor, would be 10 amps minus the 7.5 amps, which is 2.5 amps going this way. I think about them as people. There's 10 people walking down this path and 7.5 people walk this way. I guess you can't really think of half a person, maybe like 7 people and a baby go this way. And then there must be 2.5 people left to go this way. They have to split up. You can't sort of lose a person. You don't just leave them behind on the side of the path or something. All right, so I found I8, and then I know if 2.5 people are walking this way, well then all of them have to continue along that path. There's only one place to go, which is through R9 for them. So I9 must also be 2.50 amps. All the people on this path go through I9. Now I know two things at both resistors, so I can find the third. Delta V is going to be I times R, so 2.5 times 5. That gives me 12.5 volts here. And over here, delta V9 is going to be the 2.5 times 10, so that'll be 25.0 volts there. Just another quick sanity check. The total voltage drop from here down to here has to be the same whether I take this path or this path, right? So if it's a height drop of 37.5 from there to there, think about it like as a ski hill. This is the top of the ski hill, this is the bottom of the ski hill. If I take this path, just a quick short route down, it's a drop of 37.5 meters. If I take this other route, it might have 2 resistors in it, but overall the drop from here to here still has to be the same height because I start at the same point in the mountain and I end at the same point in the mountain from here to here. So this drop must also be 37.5, and we'll just check if it is. I go down 12.5 plus another 25 volts. Those add up. 12.5 plus 25 adds up to 37.5, so that drop is the same. So just another sanity check to make sure we're doing things right. Alright, the hard part is completely done. So we found all the delta V's, all the I's in every single resistor. Now I get to do the easy part. The easy part is just solving for the power through every resistor. So power, you may remember, is just I times delta V. So we're going to use this equation for every single resistor, and this part is really fast. You just get to plug them all into your calculator and fly through them. So first, P1 is going to be I1 times delta V1, which is just 10 times 28.5 or 285 Units of power are watts, so that's P1. P2 is going to be 20 volts times 10 amps, or 200 watts. P3 is 9 volts times 6 amps, which is going to be 54.0 watts. P4 is 15 times 6. Here's 15 volts times 6 amps is 90 watts. P5 down here is going to be 4 amps times 24 volts, 96 watts. P6 over here is going to be 10 volts times 10 amps, or 100 watts. P7 will be 7.5 amps times 37.5 volts is 281 watts. We can round it off with 3 significant figures. P8 is going to be 12.5, my voltage, times my current. 2.5 gives me 31.3 watts. And down here, P9 will be the 25 volts times 2.5 amps is 62.5 watts. And I've got my power everywhere in the circuit as well. Once you've solved for current, voltage, and power through every resistor, you are done.